So our next speaker is from my hometown of Silicon Valley, which is part of my NorCal chapter roots with the Mars Society. And he is a senior aerospace engineer at Maiden Space in Mountain View, California, where he works on advanced spacecraft manufacturing systems. His graduate work at Purdue was in aerospace systems and astrodynamics, and he researched propulsive Mars entry, descent, and landing vehicles. Max has previously worked for NASA and SpaceX. Please welcome Max Fagin.
Great, thank you very much. So like I said, my name is Max Fagin. Thank you to the Mars Society for inviting me to give this talk because it's one of the subjects that I am most passionate about and a subject that I don't get to talk nearly enough about because it's not part of my day-to-day job, but it is a field that I am very, very eager to see future developments in because in connection with the development of Falcon 9 and the dropping of the launch prices to low Earth orbit, there is an interesting Mars EDL connection in development of Mars EDL technology in a way to kind of burn down some of the major risks which are standing in our way on the path to Mars. Just a little bit of background about me and what I do. As was said, I currently work at Maiden Space, which is a company that deals in in-space manufacturing, so there's no explicit Mars connection to my day-to-day work. Although we do a little bit of extra regolith manufacturing on the side, working with lunar and Mars regolith simulants. But I can't talk about that today because we're talking about Mars EDL. However, my graduate work was in Mars EDL. So as a little bit of background on the problem and why it is such a subject worth studying. Mars EDL is arguably as dangerous and lethal a phase when visiting Mars as launch is. In the history of Mars exploration, there have been 14 spacecraft that have successfully made it to the top of Mars's atmosphere, and a grand total of 5 of them failed trying to get to the surface. I am counting Beagle in that. Beagle was later confirmed to have made it to the surface intact, but failed on a deployment. We don't know why yet, but either way, even if it's only 4 or 5, this is not an excellent track record. This is one of the largest hazards. This is worse than losing payloads on launch in terms of trips to Mars. So this is one of the main challenges with scaling up scaling up Mars exploration into human spaceflight levels, because all of these were much smaller vehicles than we need in order to get humans to the surface of Mars. So the challenges can kind of be broken down into 2 major phases. The first phase takes place from when the vehicle reaches the top of the atmosphere, going from exoatmospheric flight, so orbital flight, to the outer reaches of the atmosphere down to around 10 kilometers or so. And this is the high energy phase of Mars EDL. And some of the challenges of this are to dissipate the orbital energy that the vehicle has from its interplanetary transit. Surviving the atmospheric heating, the vehicle tends to develop a plasma shield, a plasma shock wave in front of it on its bow shock, which glows at the temperature of a blowtorch. And surviving the deceleration loads due to the atmospheric pressure slowing the vehicle down. Once you get below 10 kilometers and around Mach 1, 1.5 or so, then you enter a new regime of challenges, which has to do with reaching your target, landing accurately, and dissipating the last few 100 meters per second of your velocity, which you aren't really able to do aerodynamically on Mars, so you need to employ some other strategy. Now, Mars's atmosphere, as you've probably heard, is a real hard challenge to overcome. Mars is exactly in the middle ground of bad when it comes to EDL. If it were just a little bit thinner, we might conceivably be able to ignore the atmosphere, but if it were just a little bit thicker, it would be enough to, excuse me a second. It would be enough to slow it, it would be enough to help us a lot more. So the atmosphere on Mars, as you can see in this diagram, what I've done is I've shown here the atmosphere of Mars in direct comparison to the atmosphere of Earth. So this is the same vertical scale on each plot, with the highest terrain feature present on the planet shown for scale. So on Earth, with the edge of space being at about 85 kilometers. And yes, that's the correct factor. Karman's own calculations were misguided. The actual value is actually better set at around 85 kilometers, not 100 kilometers. You can read more about that in this paper here. So the edge of space is about 10 atmospheric scale heights away from us. And a scale height is defined as the altitude you have to climb in order for the thickness of the atmosphere to go down by a factor of 1 over E. While Mars, because of the planet's lower surface gravity and smaller size, has a much larger atmospheric scale height and a much closer edge of space. So you have a shorter vertical distance in which to affect all of your deceleration. If the atmosphere were a little bit taller, you could spread your deceleration out over a longer period of time. And the highest terrain feature on Mars, Olympus Mons, basically punches all the way out of the atmosphere. The top of Olympus Mons, you need to walk around wearing a spacesuit on because Mars's atmosphere is so thin. So how do we affect entry, descent, and landing on Mars? The most critical parameter to think about when you're evaluating any Mars landing architecture is the constant called the ballistic coefficient. So the ballistic coefficient is a measure of how good the vehicle is at punching through aerodynamic drag. So if you are very light and very sparse, like a piece of paper, you have a low mass and a high vehicle area, you have a low drag coefficient. And if you're very heavy or have a very low cross-sectional area, like a spear or a bullet, you have a high drag coefficient. And we parameterize this in energy space. So this is not, so these axes here are not a geometric axis. This is not the typical plot you're familiar of altitude versus downrange with a launch vehicle. This is energy space. So the altitude of the vehicle corresponds to its potential energy, and the velocity of the vehicle, its kinetic energy. So here we are at entry interface, and we need to bring the vehicle down to touchdown where it has low velocity, not zero velocity. We can touch down at a couple of meters per second and 0 altitude. Now, a vehicle with a low ballistic coefficient hits the top of the atmosphere, and the atmosphere almost immediately begins having an effect. The vehicle will very rapidly slow down over a very low altitude band, so that's what a horizontal line represents, a quick loss of velocity over a very low range of altitudes to a safe touchdown. If you increase the vehicle mass, let's say we doubled the mass to 100 kilograms per meter squared ballistic coefficient, then the vehicle is going to penetrate deeper into the atmosphere before it has a chance to slow down. It'll also have a higher terminal velocity, so your final touchdown velocity that you're going to have to get rid of with rockets or with some other solution is also going to be much higher. But if you push the mass of the vehicle up just a little bit more to, say, 200, the atmosphere doesn't really have a chance to slow the vehicle down, and you impact the surface going several times the speed of sound. Now, 200 kilometers per meter squared is not a big ballistic coefficient. Human scale ballistic coefficients, like the Mars Direct vehicle, we're still talking somewhere between 300 and 500 kilograms per meter squared. So it is a big change up from the regions where a purely ballistic vehicle can count on safe landing without additional means of deceleration. And unfortunately, the state of the art in decelerating of large vehicles like this, large ballistic vehicles, hasn't really developed much in the entire history of Mars space exploration. We haven't had a lot of development in this field. Now you might say, how can you say we've had no development in this field? What about airbags? What about the sky crane that was used on used on Curiosity? What about all these advances in Mars landing technology? Well, it turns out all of those techniques are only really. Here's the representation if we had an Apollo capsule with a human-rated ballistic coefficient on Mars landing. These numbers, by the way, are the ballistic coefficients of the vehicle. All of that development that I alluded to, all of these advanced technologies that we've invested so much time and engineering in, all of this only applies down here in the last few. In the last few hundred meters per second and the last 10 to 15 kilometers of altitude. All of this doesn't help you. It doesn't help get a large crewed vehicle down to the envelope where we could use any of these strategies. We need something else. Now, that something else, there's a lot of solutions. SpaceX has decided to solve the problem with Starship by using a lifting body. If you employ lift, the vehicle is able to decelerate as if it had a lower ballistic coefficient by arresting its descent. You can use inflatables. Inflatables reduce the effective ballistic coefficient. You can use supersonic retropropulsion, which is what I work worked on. That's where you turn the engines on even while you're traveling at supersonic speeds and get rid of several kilometers per second of velocity with engines instead of just the last few hundred meters per second. Or you can use a parachute. Now, parachutes are not typically used much beyond the 1.7 to 1.9 Mach region, and for a large crewed landing vehicle, we're looking at opening it somewhere in the Mach 3.1 to 3.9 region. And it's not clear yet whether that is whether there is some roadblock to that, or whether or not parachutes have whether or not it's going to be possible to open parachutes this big at that altitude. But we know what we need to do in order to develop a parachute like that, and that's what I'll get into in a couple of slides. So what are the hazards presented by this plot? Well, the first hazard that I alluded to was the hazard of deceleration. So this is a representation, so that we're still in altitude velocity space. These dotted lines here represent Machs 1 through 10, so decelerating hit Mach 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and touchdown. And this is the trajectory that would be flown by a notional crewed spacecraft. Ignore the last few hundred meters per second where the velocity of the model isn't really accurate there. Whereas the colors here represent the contours of G's pulled depending on how deep you penetrate into the atmosphere. So you can see if you penetrate just a little bit deeper, the G's rapidly build up. So even slight increases in ballistic coefficient, which cause you to puncture deeper into the atmosphere, can have drastic effects on your CONOPS. A typical 3 Gs is something that a healthy human can survive. That's an amusement park ride. The normal Apollo entry was about 5 Gs. Worst case scenario, human entries on the Soyuz can get up to over 8 Gs, but that's pretty paralyzing. It's difficult to expect the astronauts to be able to do anything much above that. So it's practical to keep to impose our limits around the couple of Gs limits, especially if we want to talk in terms of mass. Large numbers of human beings visiting the planet. And of course, this is an argument in favor of artificial gravity on the flight out, because G-conditioned humans that have become accustomed to 0 G, their G tolerance goes out the window. With regards to aerodynamic heating, that has a similar proportionality, except it goes as V cubed instead of V squared, so the contours are even sharper. This represents the aerodynamic heating imposed at the tip of the vehicle, where the heating is most intense, given in watts per centimeter squared as the vehicle powers through its trajectory. Now, for comparison here, about 0.1 watts per centimeter squared is ordinary sunlight. 4 or 5 watts per centimeter squared, so this lowest line right here, that's taking a hair dryer, putting it on maximum and blasting it at your palm. Whereas 100 watts per centimeter squared is, so about twice the largest number shown here, that's a welder's blowtorch. So half of a welder's blowtorch being sprayed onto the vehicle. That's the amount of heating that it needs to survive. In the parachute and in the parachute regime, where we're talking about Mach 3, Mach 4 or so around here, we're still talking the kind of heating that'll melt most low temperature materials like polymers and fabrics. So the parachute needs to be designed to accommodate non-trivial aerodynamic heating. So let's talk a little bit about the parachutes, because they're the primary obstruction to getting larger vehicles on the surface of Mars if we are restricting ourselves to using ballistic vehicles. So these are the parachute diameters of every vehicle we've flown to Mars in the past. So Mars Science Lab, the Curiosity, was the largest one, a little over 20 meters. In order to land a crewed lander on Mars, we're talking scaling up to the high 30 meters, though, if we want to get about 25 metric tons through our entry mass. And because of the drastic increase in speed, the dynamic pressure goes up by a factor of 4 or so. It's not entirely clear how much developing a parachute like this will cost. Developing Mars Science Labs, requalifying it from the Viking data from the 1970s in order to accommodate a larger spacecraft, cost about $50 million, so almost as much as a Falcon 9 launch. But we did it. We know, and the way we did it was doing high altitude testing with balloon launches and analog testing here on Earth. So it turns out that if you, so this is an example. I don't want to don't want to show the entire video here. It's a little bit long. This is an example of a test from the HIAD a couple of years ago, the High Altitude Aerodynamic Decelerator. And what they were actually testing was this inflatable aerodynamic skirt, which pops out and increases the drag of the vehicle. But what I actually want to show you is what happens when they attempted to deploy the parachute to decelerate the vehicle, which again was not a key part of the test. The parachute pops out, boom, shreds to pieces. So this vehicle was flying, the reason it was flying up here was because this is a region that aerodynamically mimics the descent conditions that a large parachute would see coming into Mars. Now again, this was not a key part of the test, so the test was the LDSD, the inflatable, but it still illustrates the difficulties of developing larger parachutes. It turned out the thing that had been missed, the thing that had been incorrectly modeled in that experiment, was the wake effects of the parachute being immersed in the turbulent wake of the leading vehicle. So the vehicle was causing wake and vortex shedding coming off the back of its aerodynamic shell, which was slapping the parachute back and forth with turbulent waves, which caused it to shred. So that was not something we could model in advance. We had to do the experiment to find out. But we do know that if we want to do an aerodynamic mimic of the conditions a vehicle at 5 to 15 kilometers on Mars is going to see, we have to climb up to a little over 70 kilometers on Earth in order to effectively test our parachutes or really any aerodynamic method of decelerating and landing on Mars. So how might we find a way to make that a little bit less expensive than the incredibly difficult method of launching on a high-altitude balloon with a rocket-assisted ascent, especially given that the LDSD payload was only a couple of tons. We need to do this with 20-ton payloads. And yes, it must be done with a vehicle of a similar mass and a similar size because aerodynamic interactions with the vehicle and the parachute are a critical part of the analysis. Well, we have Falcon 9. So this is a representative ascent profile in energy space of the Falcon 9 on a typical launch to the International Space Station. So the first stage takes it from zero velocity, zero altitude, up to about 1.6, 1.7 kilometers per second, and a little over 60 kilometers in altitude before separating and having the second stage fly the rest of the way. And then what's not shown here is the final raise to 400 kilometers, which typically happens after one full orbit, but that would be way down on the scale. So this right here is the dynamic pressure and Mach envelope that Viking was qualified to. So about Mach 1 to 1 to 3 with 200 to 800 pascals. Oh, I'm sorry, this is wrong. This should not say 3. This should say 1.9. Sorry about that. 200 to 800 pascals of dynamic pressure. And by the way, this is representative on Mars, whereas the altitude and velocity axes here are on Earth. So I'm kind of mixing my axes here. Just keep that in mind. So the Falcon 9 misses that envelope entirely. But as was mentioned, a high-mass vehicle, like a Mars Direct capsule, has to go at a much higher aerodynamic pressure and a much higher Mach number. The envelope turns out to be somewhere around here. Now we can fudge this a little bit if the vehicle ends up being slightly heavier, slightly lighter, if we're willing to pop our parachute higher in order to accommodate slightly higher inaccuracies in our touchdown zone. We can fudge this envelope around quite a bit, but the takeaway is that we think of Falcon 9 and the reusability of Falcon 9 as a new way to get 25 metric tons to LEO. But we can also think of Falcon 9 as a new way to get 104 tons to the aerodynamic regime where we want to test and develop large Mars landers. Because at this altitude, we don't have to deliver just the payload. We're also delivering the wet mass of the second stage. So there's a very, very large mass margin if we wanted to do something like this. Now, an image like this is the kind of thing that makes rocket engineers cringe. PowerPoint engineering like this is very, very dangerous. It's the reason why I am so skeptical of Kerbal Space Program. It teaches people that you can just do this. Just take this piece off and put this piece on. Just is a dirty four-letter word in aerospace engineering. If any manager asks you, why can't you just do this? But, however, assuming that there is money and engineering resources available to overcome the difficulties with launching a first stage, a Falcon 9 first stage, without its second stage on board and flying for a slightly shorter period of time before separation, there does not appear to be any roadblocks in doing something like this. So this provides us a new technique in order to reduce the cost of developing and qualifying aerodynamic methods of landing large vehicles on Mars. Now, I really do not wish to make this sound trivial. If you have a chance to go out to the SpaceX factory, take a look at the landed first stage. The thing is the size of a 15-story building, and it was designed to be exactly for one purpose only, and that one purpose was launching a second stage to carry 25 tons to low Earth orbit and then coming back for reuse. It has a very, very tightly qualified list of design criteria. And this is a complete departure from what it needs to actually do. But the key is the market is about to be flooded with flown first stages. Many of which will probably be flown up to their 10 flight design point. After which, we're going to have to find something to do with them. We can't put them all in museums. If SpaceX really does have ambitions to launch hundreds of these per year, we are going to find ourselves in the very unusual state of having an abundance of boosters, and we need to find something to do with them. So requalification of it to fly this different trajectory with the different loads is not a trivial problem. It's going to take a lot of engineering know-how, but it is cheaper. It probably will be cheaper than the development costs of flying and of requalifying a larger Martian parachute using the conventional method of a balloon-assisted launch, especially for a payload that's this big. So that's the takeaway, that the development of Falcon 9 as a reusable launch vehicle doesn't just have applications to the launch sector. It is potentially a way to burn down one of the highest risks of Mars EDL for large ballistic crewed landers. Thank you very much.
Hi. So we talked about mostly ballistic entry, and you briefly mentioned Elon Musk's plan for a more lifting body entry into the Martian atmosphere. Has there been any thought on maybe mixing the concept shown behind you and a lifting body, an actual inflatable lifting body?
An IAD? Yes, IADs are what NASA has kind of thrown their money behind. Their main downside is that because IADs deploy when you are higher and faster, they induce a much, much larger landing error. So you take what would normally be a landing error ellipse of 2 to 3 kilometers, and you make it 20 kilometers. So it is acceptable if you're going to be landing a single vehicle, or if, as in the Mars Direct architecture, you have the ability to transport your crew 100 kilometers to their return vehicle. But IADs are really not acceptable if you want to do what SpaceX does, which is repeatedly land a large payload in exactly the same spot without the need to do cross-country transit of your hardware.
This is a bit of a comment. After Max shared this idea with me, I broached it to SpaceX as to what they thought of the feasibility of this. And they said, yeah, they didn't see any particular problem with doing this, either with simply launching the first stage with a 100-ton thing on top of it. The first stage would see it as just the same thing as it was launching a second stage.
There's that dirty word, just, but...
No.
But yes,
Excuse me. The first stage does not care whether the second stage is filled with kerosene or lead. If it's the same mass, it's the same mass.
But it's
okay, and this is what SpaceX said. Okay, so I just want you to know that. And so that this is really important because we're talking about a fully reusable stage that can launch heavy payloads to hypersonic exoatmospheric conditions where they can be used to test large reentry. So and that's why Max had actually submitted this as a track talk. I invited this to be a plenary because I consider this to be an extremely important result. Because the major tall pole in sending humans to Mars that has been cited is lack of a heavy lander. And NASA said that's why we're building the Lunar Orbit Toll Booth. Well, if you lack a heavy lander, the answer to that is not to build a Lunar Orbit Toll Booth, it is to develop a heavy lander. And doing it this way, we don't have to build giant wind tunnels, we don't have to do this. There is a system, and it's a fully reusable system to launch payloads to this position. So, so there you have it. So I think this is great stuff.
Thank you. So mass-wise, thank you. So mass-wise, you're absolutely right. Falcon 9 does not care what's on top of it. The thing that terrifies me, though, is actually the aerodynamic loads. Taking something that's only 3 meters wide and making it 8 meters wide and launching with that on top, that's, there's a reason we can't just enlarge the fairings of, say, a Falcon 9 and launch a full-size vehicle that way. So not impossible. It's going to take. I just think it's going to take a lot of very smart people, which of course SpaceX has in abundance.